Hello, you're probably stuck at home with nothing to do. I'm lucky I can come to my shop and use my bridge and crane models to do stuff. So this is the small crane that we'll use today. I'll show you some of the other cranes I use with the high school kids. There's one in the back there, also a middle size. Another middle-sized one, but today we're just going to use the small one. So the boom is at a 60-degree angle. This is the boom. The load is 2 bricks, which is 9.4 pounds. So you can easily lift it. What would happen if I change the angle of the boom? So it's 60 degrees now. I want to put it down to 45. So the load hasn't changed. It's still 9.4 pounds. The only thing that changed, well, the angle of the boom. Well, let's see what happens. That's what happens. So, easiest way to understand this is think of a crane like a seesaw. Just have to have a seesaw, balance beam. So each C-clamp weighs a pound. And the distance from the fulcrum or pivot point to the end of each arm is 20 inches on both sides. Obviously this is going to work. What would happen if I leave this one here? Now we've got 2 pounds balancing 1 pound. Well, you've been on a seesaw. You have a heavy kid who's close to the pivot point, the fulcrum. The lighter kid is further away. You heard of Archimedes? He came up with a simple formula. Weight times distance has to be the same numbers on both sides. So we've got the heavy kid, let's say two clamps, 2 pounds, 10 inches away from the fulcrum. 2 times 10 is 20. 1 pound, 20 inches away. 1 times 20 is 20. So the numbers balance and everything else balances. So the trick is you measure from the fulcrum to the line of force that goes through the load. What's the line of force? Force of gravity. Gravity pulls everything straight down, right? So you measure from that line, it's an imaginary line, the shortest distance from that line to the fulcrum. So, here's that line and here's the fulcrum. I could measure, well, that's from the line to the fulcrum, but that's 10 inches. Well, whatever it is, let's say it's 15 inches. It's not the shortest distance. The shortest distance from the line of force to the fulcrum would be this one, which will come very handy in a minute. So, I'm going to change the angle of one of these arms to 60 degrees. Technical difficulties. Okay. So remember the distance from the fulcrum to the end of each arm is 20 inches. That's 20 inches. That's 20 inches, that's 20 inches. Well, it balances, but do the numbers balance? 1 times 20 is 20. 2 times 20 is 40. So we got something wrong with the numbers. So here's how you do it. Remember I said you go from the line of force. Line of force, the shortest distance from that line to the pivot point is right here. That's at 20 inches. So here's 20 inches again, but the line of force, the shortest distance from that line to the fulcrum is here. So if this is 20 times 1 is 20, it's got to be 20 on this side, right? So 2 pounds times how many inches gives you 20 inch-pounds? 10. So this distance is 10 inches. 10 times 2 is 20. 1 times 20 is 20. So it balances and the numbers balance. Now we get back to the crane. I'm going to go back to 60 degrees. .4 pounds for the load. Okay, so everything is measured from the pivot point, the fulcrum, which is right there. Here we go. So there's the fulcrum. That's where everything's going to pivot. So on one side, think of this as a balance beam. On this side of the balance beam is the weight of the crane body, which weighs 10¼ pounds. And we measure from the line of force of the crane to the fulcrum. Now the line of force goes through the center of gravity, which I haven't told you about yet. So where would the center of gravity of that be? It's about 14½ inches long, and all the material in the wood is evenly distributed. So the center of gravity would probably be in the middle. So an easiest way to find the center of gravity is just balance it on something like this. That'll tell you the center of gravity. In this case, it's half of 14¼ which is 7 1/8. That's the center of gravity. So I did the same thing with the crane. Before I put the boom on, I balanced it on a pipe, and the center of gravity, well, the crane is 32 inches long, the crane body. The whole thing is the crane, but the crane body is everything once you take out the boom. So the center of gravity of the crane is 17 inches from the pivot point. So the line of force, the shortest distance between the line of force, that imaginary line, and the pivot point is right here, 17 inches. I didn't tell you what torque is, did I? Whenever you have a force that causes rotation, that's called torque. Just like the weight or the force causes the whole thing to rotate. When you open a door, you push on one end of it, it rotates around the hinge. With a crane, the torque of the load wants to rotate the whole crane clockwise or counterclockwise, and the weight of the crane body wants to counteract that. So, back to this. So on one side of the pivot point, we have the weight of the crane, weight times distance. Remember from the seesaw? Here's the weight, here's the distance from the line of force. 10 1/4 pounds times 17 inches is 100 and something. Where are we? Is 174 inch-pounds. So everything on this side of the fulcrum, I always use a triangle to denote the fulcrum. Everything on this side is 174.25 inch-pounds. So on the other side of the fulcrum is the load, 9.4 pounds. Weight times distance, right? We have the weight, we need the distance. The distance from the line of force of the load, that imaginary line, to the pivot point of the boom. Right? No, it's the pivot point down here. Well, I'll have to fix that. But first we got to use this right triangle. And it's a $30, $60, $90 triangle. You learned about right triangles yet? So, here's the right triangle, here's the hypotenuse, here's the short side, here's the long side. And this is basically what we have here. The hypotenuse is going to be the boom. The short side is the distance, that's what we're looking for. The distance from the pivot point to the line of force. Now I used a 60-degree angle for a reason. In every 30, 60, 90 triangle, the short side is always half the hypotenuse. 9 1/8 is half of 18 1/4. Here's another 30, 60, 90, same thing. 7 is half of 14. So, we've got this 30, 60, 90 triangle. The hypotenuse is 46 inches, which means the short side, which is what we're looking for, is 23 inches. And I'll find the here's the here we go. So this distance from here to here is half of the hypotenuse, which is 46, and this is 23. But you notice that the boom, the pivot point for the boom is way back there. It's about 9 inches from the front, from the fulcrum. So we have to subtract 9 or 10 inches. From here to here is 23. We have to subtract 10 because we're only interested in everything on this side of the fulcrum. So 23 minus 10 is 13. 13 times 10. So we get back to weight times distance. The weight is 9.4, the distance is 13. That gives us 122 inch-pounds, which is less than 174. Everything from here over is 174 inch-pounds. Everything from here to the load is 122. This is bigger than this, so didn't tip over. The next video we'll change the boom to a 45-degree angle, Well, you know what happens, it's gonna tip over. But now we gotta run the numbers and understand why.